website. So if Barry, take it away.
Thank you, Enrique. That's kind of the good overview, and I'm going to go ahead and take my video off so I'm not just a distraction. And we want to get into this. I've been doing this for a long time. Some of you who have known me all the way back into my Zender days. So I started with Zender America and actually was employee number one at Zender America in 2001, about a week after 9/11.
Hmm.
And I spent 15 years at Zender, and then in 2016, March of 2016, went to work for Ventacity, which at the time was a startup company out of Oregon. And I've been doing ventilation in high performance buildings for a very long time. And I think it was 2008, the first Passive House conference I went to. I loaded a Zender ERV into the back of my car and drove out to Illinois to a Passive House event, and I've been doing it ever since. And one of the things that we have had a challenge on in the ventilation side of HVAC was just the recognition of the importance of ventilation in system performance and in whole building performance. And I've been frustrated, I think would be a good word, for a long time, that the lack of recognition of what the importance of the efficiency and what a little bit of better efficiency can mean to whole building efficiency and energy use. And so this development of this new testing and ratings procedures by CSA, Comfort or the Canadian Standards Association, development of this new testing and ratings procedure will allow us to do systems approaches to a whole HVAC system on a seasonal COP basis and really get a good metric that you can apply to energy modeling and other things. To take you through, I'll start through and I'm going to kind of give a little background and what these testing and ratings procedures look like. So you've got we've been doing these retrofit projects for, as I mentioned, a long time. With Ventacity, we've been doing projects retrofitting existing buildings with what we call a very high efficiency HVAC. So it's typically heat pumps combined with Ventacity ERVs or HRVs, typically replacing rooftop units, gas pack RTUs, and dramatically reducing the energy in these buildings. This is a project we did in Tarrytown, New York. It's a 71,000 square foot office building, 4 stories. We took all this old dual deck RTUs off the roof and replaced it. These are the heat pumps that were simultaneously set up and running before they removed this and then put in the ERVs, leveraging existing ductwork. Before we did this project, this was done through the Con Ed utility with incentives. And so we used AHRI, which was the testing and data that they used for efficiency with heat pumps and ERVs, simple inputs, and the old AHRI testing and ratings procedures. And the model that was done, and this is a very extensive model. They charged $20,000 to do this model to submit to Con Ed to get the incentives. And so they went through a code minimum retrofit, just replacing the existing RTUs versus this DOAS ERV and VRF. So very high efficiency ERVs and VRF heat pump systems. Total cost was $300,000 incremental cost over code minimum retrofit. And the simple payback was 29 years on the total $2 million. They were saying total annual savings about $61,700 when we retrofitted this. The incremental cost, payback on the incremental cost was only 3 years. They were looking at, you know, $300,000. The incentive was $140,000, so bring it down to $160,000. So they had a 3-year payback on that, and that looked pretty attractive to the building owner, so he went for it. And, you can see here electricity and natural gas reduction that they had anticipated here, 181,000 kilowatt hours and 29,000 therms. That's what they modeled. Here's what we actually did. Modeled, actual. $20,000 for a model that missed by 300%. Not great. The incentive should have been $400,000. Con Ed gave them $140,000. This is something I've been dealing with for a very long time. So they anticipated they'd save $60,000 a year. The first year they saved over $200,000 in energy costs. So dramatically different than what they had anticipated. And this has been the boon of our existence in the retrofit arena, where you're dealing with incentives based on how much energy they anticipate saving. That's what they give them for savings. It would be much better if they gave them the incentive a year or two later after what we actually saved. But the modeling has been challenging. The Northwest Energy Efficiency Alliance, where we started doing these retrofits, and they developed an actual specification to a model for retrofitting buildings, commercial buildings. They call it VHE, very high efficiency. They call it VHE DOAS. We call it VHE HVAC retrofits. And, this is the kind of savings we got on that building. So we took demand, which is another serious aspect that they underestimated. Demand went from 519 to 366, a dramatic reduction. And demand charges, they got their electricity as low as 4 cents a kilowatt hour in New York because of the demand that we reduced demand charges. So dramatic reduction, not modeled. And so, now we're asking, why did that model so grossly underestimate the savings? And in a nutshell, it's because the system efficiency, the combined heat pumps and HRVs or ERVs, when you put them all together as an HVAC system, it is much greater than their parts. And this is where you would look at doing a system COP. So it started first, the CSA, in combination with NEA, the Northwest Energy Efficiency Alliance, developed these new testing and ratings procedures. SPE 07 here was released in 2023, and that is for heat pumps. And then CSA SPE 18, just released, is HRVs and ERVs. This is for the heat pumps. This is what it looks like. So what they're doing, what you have at the top, these are, I will apologize, it's a lot of charts with small numbers, so I'll try to talk you through it. Enrique and I had this conversation. We'll try to, have you understand this. But what this is at the top is all the different climate zones. And so they're testing heat pumps to these different climate zones, and you'll get a system COP, or a seasonal COP, excuse me, for each one of these. And obviously the subarctic, those are temperature ranges that are very low, and you're going to have a lower COP. It's 1.88 in the subarctic. When you get into hot, humid, it's all the way up to a COP of 4. All right, so it's very efficient for a heat pump to run cooling with a small delta T. It's also very high in, marine, 4.17 COP. So that's what this chart shows, is the COPs at those different temperatures. So this is your outside air temperatures, and these are test points that they do. So they did the old AHRI testing for heat pumps was a single temperature point, 43 degrees, I believe, and that's what they tested them at full load. What this testing rate procedure does is it'll be part load. It'll be full load when it's in testing at this minus 20 here, or minus 15, I believe, is this point. So it'll be operating close to full load. But when it's operating in these mid ranges, when it's at 40 degrees, 45 degrees, it's going to be operating at a very different load. It's partial load. And that's how pumps actually operate. So they get all these different data points for these different temperatures. And this is heating and this is cooling. So they're getting the COPs on cooling. All right. And so they chart these, and this is subarctic, very cold, cold, marine, and so forth. These are your calculations. And then what you have here is what they call bin, the bin data. That's the percentage of time that you're going to operate within those temperature ranges for each climate zone. Everybody know how those work, or do you know how those work? Bin data will be, so if you're in a cold, dry, heating season temperature bins, cold, dry, you're going to be in a percentage at each one of these different temperatures. These will all add up to 100%. So you take a percentage at this point, a percentage at this point, a percentage at this point, and combine that, and you have the average where that mean COP is going to be for heating and then for cooling. The key is more data points, more test points, and more accurate information on how that heat pump is going to operate throughout the seasons in those different locations. So it allows you to have a much more accurate than the old testing and ratings procedures, a much more accurate picture of performance in each location. So it's load-based, climate-specific testing and rating. SPE 18, which was just released in the fall of 2024, so about 6 months ago, they published that for HRVs and ERVs, is doing the same kind of thing. One of the problems we've had in the ventilation world is that AHRI 1060, which is the commercial testing and ratings procedure, and CSA 439, which is residential, 300 CFM or below, that the Home Ventilating Institute, HVI, uses. These are some points that will show the differences. AHRI and CSA 439 allow for mass flow imbalance. What that means is you can imbalance your supply and return flows when you're testing. And I'll show you what that means in a minute. You can do dramatically positive looking things by imbalancing airflow because it's called a mass flow imbalance. If you have more in the wintertime testing in low temperatures, if you have more warm air leaving than cold air coming in, that's more energy on the exhaust side that's going to transfer energy to the incoming air side, and you're going to appear to be better on your supply air. So you can make it look good. The problem is, in the real world, more energy leaving than it gets transferred coming in means that a part of that energy that's leaving is literally leaving the building. If you have warm air leaving your building, that's energy leaving your building. And so that's an important, probably the most important thing is that CSA SPE 18 mass flow balance within 5%. It must be mass flow imbalance. Primary testing AHRI is just the core wheels. They're not testing the whole box. It's like testing an engine, putting an engine on a workbench and saying, yeah, it's 300 horsepower. It gets 20 miles to a gallon. Well, how do you know that? You have to put it in the car and run it on a, test track to determine what the actual. They're testing a core, you're testing a heat exchanger, that isn't telling you much of anything. So, and they limit it to 70 and 100% flows. So they're only testing those 2 points. And there are two data points for temperature, heating and cooling. 0C, and I believe it's 25C, what they're testing for efficiency. And CSA 439 for smaller residential, 2 or 3 data points. They do a, cooling, high cooling temperature. They do a minus 25C, which is about minus, I believe, 15F for cold climates. They do 0C, 32 degrees Fahrenheit for standard, and then they do 25C. The other thing is they have a very high failure rate for challenge testing. I learned that when I was with Zender and we were a member of the HVI, and at a meeting, they kind of fessed up and said, yeah, 80% of our challenge tests fail, which means that the units that they tested were doctored, and the challenge test, when they go out and buy one off the shelf and put it into the lab and test it, it has to be within 10% on the metrics they're failing. So not accurate. This doesn't allow, the new CSA SPE 18 doesn't allow for a lot of monkeying around with that stuff. So they're using 6 data points, which kind of represents those 6 climate zones. Accounts for that. They also account for frost control in cold climates. So when they're testing to those low temperature data points, frost control comes into account, and they'll test that. And if you're using electric defrost or any other metrics that contributes to the energy in, so reduces the COP at that test point, that'll be reflected there and play into the whole efficiency over the whole thing. They also test indoor and outdoor. So if you have a unit that's going to go on the roof on a curb, they test it outdoors. So if you're testing it, 32 degrees or minus 10 degrees or whatever it is, that unit is outside in a 32 degree or minus 10 degree space to test for its efficiency. Same if it's 90 degrees outside Fahrenheit, it's tested outdoors in a 90-degree room, call it. That's not done with AHRI or CSA 439. They do it in a laboratory. So those are all different and much better metrics that they're getting to put into the model. AHRI, I mentioned the mass flow imbalance, and this is real stuff that was done. So you have here a flow rate outdoor 1400 CFM supply and 1110 CFM return.
Excuse me, Barry, is it possible for you to zoom a little bit more the charts so we can see better the numbers?
Well, I can give you what you need to know. The numbers, the important ones are on the right here. Okay. So your
Okay.
outside air is 23 degrees, your return air is 70 degrees, which is a differential of 54.6. I don't know why that is. It's yeah, it should be 57 or 47. Yeah, 47 degrees differential here. Oh yeah, the 54.6 is there. So, the bottom line is you take your differential and your total difference, and you're getting 67% is the actual from the delivered temperature here of 54 degrees. But down here, They show you sensible effectiveness percent, 84.9%. And I was like, how did they get to that? And this is what they've been giving to people to use, engineers. It's 84.9%. Turns out what they did was take the imbalance percentage between 1400 and 1110 and add that back into the 67, and they got us to 84.9. Does anybody understand that? If you don't, I totally understand it, that you don't understand it. It's not data, it's manipulation of data. We did a little selection with Ventacity. Again, don't worry about these small numbers. We did the same thing with a unit, those same temperatures, with an imbalance, so running 1400 and 1110, we came up with 79%. This is off actual testing data. So the difference between, 67 and 79, that's a very, very substantial difference. If you ran it in a mass flow balance at 1400 CFM each, it goes from that 79 to 84%. It's one of the reasons why we recommend balanced flows on ERVs and HRVs. But this is the kind of thing that AHRI and HVI were allowing with mass flow imbalance testing and reporting out efficiency numbers that were grossly exaggerated. What should have been 67% here is actual, what they're doing is being reported at 85%. So this new testing and radius procedure, mass flow balance, and all of these data points. So you're testing at 95 Fahrenheit, 86 Fahrenheit, 50, 32, 14, and minus 13. 6 data points that they're measuring at. Those are then applied to these climates, and then you put them into a chart. One last thing I'll mention is there's another type of heat recovery or energy recovery ventilator that are out there. They call them fixed bed regenerators. They use a heat sink, usually steel or ceramic, where they run air in one direction. So if you have cold air coming in and two streams, cold air is coming in on one side and warm air exhausting on the other side, they run them for a time and then they reverse the flow. So the warm air leaving warms up that metal heat sink. They reverse the flow and then it gives up that heat back into the cold air coming in. So they're reversing direction and using a heat exchanger as a heat sink in the middle. There have been some really, really high claims of efficiency by some of these manufacturers. I've heard up over 90%. And then I found out that one of the Canadian hydro organizations, one of the Canadian utilities, put one into their lab and tested it, and it was closer to 60 based on continuous data. At one point in that, immediately after changing direction, it may be 90%. But as you can imagine, it's going to the delta T between the incoming air and that heat sink is going to be smaller and smaller as it runs over it and draws heat out of it. And so it may start at 90, but where does it end up before it turns direction and goes the other way? So they do this with 30 times per recovery period. They take temperature measurements and then they'll average those out to determine what the actual heat recovery is on those fixed bed regenerator units. So there is a testing and radius procedure for those. Don't even try to look at this. This is just to tell you that there is such a thing as a very complex, call it a spreadsheet, that is a modeling tool. Important down here at the bottom, compliments of my brother, older, smarter brother, Charlie Stevens. Charlie worked at NIA when they started all of this development of these new testing and ratings procedures and had been involved with them through the whole process with CSA and NIA. So Charlie developed a spreadsheet that you could apply these numbers to come up with whole system COP. So I'm going to take you through it one bit at a time. So what you've got on the left here is all of the different temperature ranges for the climate zone and temperatures. And then you've got here your climate zones. And so you'll come up with, in very cold, it's going to be 0.4% is going to be at minus 23, 0.6% at minus 8, and so forth, all the way down to 13, 14% at 37, and so forth. So you've got very cold, cold. Mixed is going to be mostly in the higher temperatures. Everybody follow? So it breaks it out so that you can apply a percentage of those different testing points, and it will look, I'll show you this, it'll look like this. So it'll have the COP, and this is for the ERV on this section. And then you've got different heating, cooling systems that are applying their COP to those same temperature ranges as a percentage. So you've got a VRF as a COP at minus 10 to minus 15 is 1. A lot of you know that. They have they're running electric resistance or a very low COP in very cold climates. And then it's going to increase, goes all the way up to, at greater than 54 degrees, it's almost 5 on the COP. All right. Gas spec RTU is not very efficient, 0.78 all the way down to 0.67. Electric resistance RTU is basically 1, 0.98 here. Heat pump RTU will, in low temperatures, be very low because it doesn't operate below certain temperatures. So its electric resistance up to this point and then is got a better COP. So that's your heating system performance. Here's the HRV system performance. Obviously, when you have a low delta T, you're not going to be recovering as much energy, but your fans are running 100%. Whereas if you're very cold temperatures, you're capturing a lot of energy because you have a very large delta T and are capturing more energy for the same fan power. All right. So then you take that total COP and you combine the percentages with those different cold, dry, cold, humid. These are your percentages of the time that you're operating in those temperature ranges, and you can apply these COPs at those different ones. And in the ultimate, the ventilation seasonal COP in these different temperatures with VRF, slightly different than it would be with a heat pump RTU and so forth. So the ventilation COP, the heating system COP, let's just look at cold humid with VRF. The ventilation comes out 10.7, the heating 3.37, and then you have to load it. You have an HVAC system, so heating, cooling, ventilation. seasonally you have heating and ventilation. So you take the percentage of your total load. Is it 20%, 30%, 40% ventilation and the balance heating? And that will vary. What happens when you build a passive house? What happens to the heating and cooling loads? They get really small. So we're loading combined system COP at 20% ventilation, 30, 25, 30%, 35% ventilation. It may well be that in a passive house, the ventilation component of HVAC load could be above 50%, even up to 70%, because your heating cooling loads become so small in an extremely tight, well-insulated building. So ventilation COP becomes a really big factor on your whole system because it's loaded and favored toward the ventilation side in a bigger percentage. So you take the combined ventilation and heating with, say, ventilation at 30%, and you have a system COP of 5.56. If the heating or ventilation load is smaller, 20%, it's 4.83. Does everybody follow how this works? No?
I think so.
I need to go back. Ventilation COP, heating system COP, percentage load, and you come up with these numbers. You
So
see that?
it's a prorated one.
It's prorated here at 20% of ventilation load, 25, 30, 35% of ventilation load. So the difference between a VRF system and a gas pack RTU system, 5.3 to 3.16. Significant difference in the total COP. Let's go a little further. I did a marine climate. We've had our friends in California that don't feel that ventilation, HRVs and ERVs, because it's temperate and they don't have that much difference in temperature between outside and inside, that they really have a big value. But we did this calculation with ventilation COP in a marine climate, which is a good part of California. The ventilation COP with VRF is 8.2 combined heating system of almost 4, gives you a system COP at 30% ventilation load of 5.24. If you're not using any ventilation, you'd have, if you're just doing outside air, opening windows, you have a COP of 0 on your ventilation, and your heating is 3.96. So your total system would be, I don't know the number here, but it would be below this because your outside air load has to be met by the heat pump. So it is going to save significantly by doing a combined system.
There is a question here. What is the percentage ventilation load? Ventilation load divided by total load?
The percentage ventilation load is, okay, it's HVAC. So you have the heating. In the winter, you have heating and you have ventilation. To come up with that number is a little bit of a challenge because, we can do the numbers, okay, bringing direct outside air at so many CFM with call it a COP of 0, you're going to figure out how much energy is going to be needed to bring outside air to room temperature. Another way to look at that is if you use a bath fan on a 0°C, 32-degree day, and you're blowing 20°C out of the building, you have a delta T of 20 degrees C. I can do the load on that because what's going to replace the 50 CFM that you're blowing with a bath fan of 20 C air out of the building. Actually, let's use 68 because or 70 because 70 degrees because it's 1.08 BTUs per cubic foot times the delta T. So the difference between 32 and 72, call it, is 40 degrees times 1.08 times 50 CFM, and that's the BTUs you're blowing out of your house. And what's going to replace it is what comes in through the cracks because you're depressurizing the house. You're going to replace it with 32-degree air. That's my outside air load. The energy I'm blowing out with that bath fan is my outside air load. Does that help? So whatever the ventilation requirement is, you look at, okay, we've got this building and it has, 3,000 CFM that we're doing to ventilate the building. Well, that 3,000 CFM is going to be the outside air load. Heating it or cooling it to inside temperature is the amount of energy it would take for that 3,000 CFM throughout that seasonal difference in temperatures. Using heat recovery, I reduce that outside air load dramatically.
Yeah, there is another question. Is that divided by a total of ventilation and other loads? Yes. I think what you're talking about is the total load of the losses by
Heating, cooling,
transmission.
ventilation is
Yeah,
your total load. Yeah,
correct. But that the way you calculate it is the total load that you have is the ones that you have through the envelope plus the ventilation load.
the remaining ventilation load after heat recovery, exactly.
So that is the total load that you have, and that's why you get the percentage of 30 or 50%,
Exactly.
depending. And if you're talking about a passive house where you have a very low losses through the envelope, then the ventilation load is significantly higher uh,
Exactly.
in that respect. Yeah. So
That's
did
correct.
that answer your question, Andy?
Yeah. This is a close up of that. So here's your ventilation in total. Now let's look at modeling HVAC system, VRF, and an HRV, ERV, and look at the differences. Difference between a 67% efficient, call it ERV, with 1.2 watts per CFM. So that's your COP is going to be determined by the energy you recover and the amount of energy you use to recover it. Versus 82% at 0.6 watts per CFM, passive house level of efficiency. So your heating COP is going to be the same. It's VRF, 3.37. Cooling COP, 6.03 for the heat pump. But the ventilation COP heating during the heating season is 6.7, cooling 3.4. All right. Heating season at this level, the COP is 14.4 in heating and 4.0 in cooling. That's not unusual that cooling is going to be closer together, not as much efficiency because during cooling season, the delta T between 90 degrees and 70 degrees is only 20 degrees, whereas in the wintertime in cold climates, that 20 degrees could be, in cooling during the winter, you've got 30 degrees and 7 degrees. It's 40. It's twice as much delta T between outside and inside. So you're going to have higher recovery rates, much more energy recovered for the same fan power.
There's another question. How does that translate into the total heat, cooling, ventilation, energy over a year?
Well, this is the way to look at it, is the difference between, this is a system COP here at this level of efficiency. On the only difference here is the ERV goes from 4.38 to 6.68 in heating, and 5.24. There's not a huge difference in cooling. So over a year, it's primarily going to be the heating season, but it's a 50% increase. This is going to be using significantly less energy than this system from a system standpoint.
There is another question. What is an example of a system on the market that delivers 14 plus ventilation COP?
Ventacity, right here. This is Ventacity. There are others. There are a couple of Passive House certified brands, and in smaller units, you'd be looking at Zender and Brink, and there are a few now. Passive House level of efficiency.
So is that significant? There is another question. We need to see that in the context of the total energy used to answer the why bother question.
Run that by me again.
Do you want to ask that? Unmute yourself, Andy, and ask it yourself.
Yeah. So obviously the COP is way better, but what's the net result in total energy use of the building that you may model here, in terms of annual energy use? I mean, it'd be twice as much. Let's say it's 50% better, which is what it looks like from these COPs on the ventilation side. But what does that mean in terms? Is that like 20 kilowatt hours a year, 200, 2,000,
Well,
20,000?
it's going to be 50% less energy.
Right. But is that 50% less than 100 or 50% less than 10,000?
Well, it depends on whatever the building is using. You're going to reduce it by that
Yeah.
amount.
I guess my point is, if you've got a very small load to start with, reducing it by 50% saves you a relatively small amount, perhaps compared to the cost of the increased efficiency of the system. So that's why you
The
need to see
difference
it in the
between this
context
and
of the
this,
total. That's why you need to
yeah,
see it in the total context of the total energy use for the building.
yeah.
Because for some buildings, this will make a huge difference. In other buildings, it won't make that much difference.
Residential, you're probably talking about a lesser difference.
Right.
But again, it's relative. A residential HRV or ERV is not a huge investment. To go from this to this is not huge. We're typically in the commercial realm, we typically look at 2 to 3 years payback between going from this to this on the energy side. That's pretty good. 2 to 3 years on a piece of equipment that lasts for at least 20. This is another way to look at it. Electric heating and no cooling. I'm seeing these projects here in Maine, and it's been, quite honestly, it's been upsetting that we've gotten value engineered off of these projects. And we were on the project and it ends up with this. And we're going from, doing those same numbers, we're going from a system COP heating is, there's no cooling. It's just the ventilation left, but goes from 5 to 8.89. So that's this building is going to use half as much energy, almost nearly half as much energy as this building. That's a pretty big deal, at least for 6 months of the year. And these have been passive house projects that are using large quantities of ventilation, and they're going from this to this, or this to this, when they value engineer it. And at electric rates of 25 cents a kilowatt hour, that adds up pretty darn quick. So, and this is one thing here is this is at 50% heating and cooling load, 50% outside air. This is at 70% heating, cooling, 30% outside air. That's more passive house is what I was looking at. Electric heating, no cooling. You're looking at here 1.44 to 4.88. It's a 300% increase. So in an older building, less insulated and tight. But when you go to passive house, that's still, this is passive house from 1.74 to 7.49. That's a 4%, 400%. Yeah, excuse me. This one is, that's the ultimate right there, is going in a 50-50 electric heating, no cooling. They're doing this in Maine. We're talking about 400% increase. Does everybody follow that? Getting the gist?
Yep.
Any questions?
Just to pick a little bit, that's not a 400% increase. The 749 is 400% of 1.74, but your increase is 300%.
Well, it's 4 times better.
That's true.
So it's going to use 25% as much energy. That's pretty big. That's dramatic.
Agreed.
And this is the thing that has been falling through the cracks. When people look at 67% to 82%, they're saying, well, that's 15%. It's however you want to calculate it, 300 to 400%, not 15%. It's a massive difference. This is where the frustration has been, and when you kind of understand the importance of ventilation efficiency, especially in passive house. And this new testing and ratings procedure, I think, will help people fully understand and specify products and also model better so we can get a much better modeling on what the performance of these will be. Just to give you an idea, we've done projects. This is a school, just to finish up, I have just a few minutes, but this was a project we looked at. It was a school out in Washington State, just south of Seattle. And we did all the numbers on it because this was during COVID. They had 6 3,000 CFM HRVs in this case they needed. They couldn't get them. What was specified, conventional HRVs, because of the lead times during COVID, it was 52 weeks or something, a year advance. We had them in stock. They had to justify the cost difference. There was an increase in cost. So we did the calculation of COP of 5 versus a COP of 10.2, translated into how much energy was recovered and used. At 15 cents a kilowatt hour, we saved them about $140,000 over 10 years, which was how long they were borrowing the money. The payback on that was about 3 years, the differential cost. So they were able to understand that this solution was using half as much energy as this solution to provide their ventilation. And so it was easy to do. This is a project in New York City. We looked at the same thing, and just the bottom line here, we looked at the existing as using boilers and chillers and perimeter radiators and air handlers with raw air drawn into a mechanical room, picked up by the air handler, heated or cooled, and distributed into each floor of a 50-story office building. So we were looking at a COP of 0.75 versus a system COP of 5.3. Based on this, we could determine that they would save about $1 million a year in energy costs, and they're going to pay, starting this year, $1 million penalty on local law 97 requirements to reduce your carbon footprint and energy in buildings in New York City. And a failure to do anything means they'll start paying a fine of, it starts at $1 million. So they'll start losing $2 million a year this year over if they had spent the money, but it was a fairly good investment to do that, floor by floor, using heat pumps and a ERV. But we were able to model it with this and really get a good idea of what the savings were. And we've been doing this, taking rooftop units off the roof, replacing them with heat pumps and very high efficiency Ventacity HRVs and ERVs, go from a system COP of 1 to about 5. And, looks like this. And system COPs of 5, give or take, depending on the climate. And this is the kind of savings we get, 6, 70, 80% savings on these projects. So that modeling has been somewhat predictive, whereas conventional modeling has underestimated the savings dramatically, very consistently on these projects. So looking at it from a system COP perspective, we've had a better look. And this is, demand reduction is dramatic. And this one was 84%, I believe, is the HVAC energy savings. Looks like that.
Were those buildings retrofitted to high?
These are retrofitted, typical rooftop units, RTUs of one form or another. This one was dual deck RTUs, they're known as. Very, we call this worst to first. So taking dual deck RTUs off and replacing it with VRF heat pumps and Ventacity ERVs, or in this case was HRVs out in Seattle, and 84% HVAC energy savings.
What I'm referring to is whether the envelope was retrofitted. Or,
wasn't touched.
Okay.
Was not touched. All they did was replace the HVAC. So yeah, we've been doing a lot of.
Regardless whether it's a high performance building or standard building, the relevance of the efficiency of the ventilation system is critical.
Absolutely, and I would say, as I showed there, the better the envelope, the more critical the ventilation efficiency is, because it's going to be a larger component. Now, the total energy is going to be lower. Naturally, and everybody knows passive house, the total energy is much lower. But I think what has happened is we've underappreciated the efficiency of the ventilation, HRVs and ERVs, in the total HVAC modeling on those projects and the impact that it has. If you build a great building, putting modest efficiency ERVs or HRVs gives away a lot of what you've done.
Correct.
And it's demonstrated when you look at testing and ratings procedures that properly analyze and provide inputs on the heating, cooling, and ventilation in such a way as these systems do. All right.
Right.
Any
Any other
questions?
questions? Feel free and unmute yourself and put the questions there.
The other thing is, if anybody wants continuing education credit for call it a lunch and learn, we work with the Practicing Institute of Engineering, and you can send it to barry@ventacity.com. Just send me an email, and I will provide you with a certificate and then report it to PIE. All right.
I have a question, and how is this how is this new procedure for testing EHRVs making it into various modeling efforts, like modeling software or code or anything like that?
Yeah, it probably won't happen really fast, Andy, because they have to get enough equipment into through the process. They're just doing some preliminary testing. As a matter of fact, Ventacity is planning, we're having one of our units tested to this completed and published testing and ratings procedure by Purdue University's in their lab is happening in the next 2 weeks. And they're going to start testing some equipment to that testing and ratings procedure. And then after that, you got to get enough equipment into the system so that you have data that you can work with to do the modeling. So in Canada, we are anticipating that it'll start with the VRF because it was published in 23. The word is that Canada is going to adopt CSA, SPE 07 as their standard probably next year.
You getting a lot of pushback from HVI?
Well, sure. Yeah, HVI just came out with a new testing and ratings procedure, but as I've said, it's easily manipulated and not really a good standard. And I worked intimately. I mean, I spent time in the lab doing the testing for HVI, and through the whole process. At one point, our testing engineer from Zender came over from Holland and went to the lab with me in Mississauga. It's Exava's lab. And I got a printout for one of the Zender units that was 102% efficient. So what's that tell?
Patent that.
Huh?
You ought to patent that. Sounds like perpetual motion.
Yeah.
And Harry Vedkamp's his name, and Harry was extremely brilliant. He actually was there to train the guys at the Exava lab in doing passive house certification testing for HRVs and ERVs. And he was watching him in action was, really interesting. He's a brilliant guy. But he said, "Oh yeah, watch this," and he just sits at their keyboard and kind of programs in what he wanted to do for the parameters, and then, an hour later we came and printed out the results of the test, and there it was, 102% efficient. He's like, "Yep, that's what you can do if you know what you're doing." So that's a problem. I was going to use that. I was going to give that to Passive House. If you want to use HVI, here's our number.
Thanks for your presentation and for this work. And thanks, Enrique.
Well, I'm
Thank you.
just getting used to figuring out how to present this, so it's not as clear as it might be, but I thought it's interesting and it's exciting that it's happening. I think it's going to change things over the next coming year or two and allow us to do much better modeling. So,
yeah, thank you very much, Barry. It was great.
Thank you, everybody.
Okay, until the next time, thank you very much for being with us, and have a good rest of the day.
Thank you.